Okay, so very good evening, everyone, and welcome to the NPTEL 12th live interactive session on the course Mechanical Behavior of Materials Part 1. So, this will be our last live interactive session for this course, and the course instructor for this course are Dr. Sushant Sekhar and Dr. Sudhanshu Sekhar Singh from the Department of Material Science and Engineering at IIT Kanpur. And myself, Shubham Jaiswal, I am a research scholar in the Department of Material Science and Engineering at IIT Kanpur. So in today's live interactive session, we will be going to we will quickly recapitulate what are the things has been covered in week 12, followed by some concept related questions, which will in turn will help you to solve your weekly assignment. And if anyone has doubt in this session, so they can clarify in this session itself, as this will be the last session for this course. So the last week we began with the concept known as hardness testing. Okay, so what is hardness testing, or what do you mean by hardness? So hardness is a measure of material's response, or we can say the resistance to a localized plastic deformation on the surface. So why do we need hardness if we have other methods like tensile testing? So the hardness testing gives the response of a material to a localized plastic deformation, that too on the surface. And this is very simple and inexpensive as compared to other techniques. And it is as we will be doing the indentation, means performing the hardness testing on some localized area. So we can say it is a non-destructive testing, and it gives the indication to that of the strength. So if we see, we begin last week with the hardness testing. So it is a measure of or materials response, or we can say resistance to a localized plastic deformation on the surface. So what are the different types of hardness testing? So there are mainly three types. One is the scratch hardness, second one is the rebound hardness, and third one is the indentation hardness. So in scratch hardness, what we do, we will check the ability of one material to scratch over the other. And in rebound hardness, so we will drop some weight or some hammer on the sample, and we will see how much it is rebound. And in the indentation testing, we will do the indentation on the sample. So coming to the types of hardness test. So first one we have, that is scratch test. Second we have rebound hardness. Let me write this as scratch hardness. Scratch hardness. And third one we have indentation hardness. Okay. And we have discussed what are the features of the hardness testing. One is it is simple and inexpensive comparatively. Okay. The second one, it is non-destructive. And the third one is it gives the indication of the strength. So if you need any rough idea about the strength of the material, so instead of doing the tensile, you can simply roughly you can give the estimate from the hardness test. So first we'll see the scratch test. Okay, so it is based on the Mohr scale. So what he did, he took a 10 different compounds and he gave them the hardness number. Okay, like he gave one for the top and up to 10 he gave the hardness number and 10 for the diamond. So what we do in this test, so we'll take a material and we'll try to scratch it with the our what are the this 10 material that we have. So if I want to know the hardness of this pencil, so what I will do, so simply I can try with my nail. Okay, so if it is scratching, so it means its hardness is less than that of my fingernail. Or suppose if it is not, it means its hardness is greater than that of my fingernail. So suppose if I scratch with some other material, so if it is scratching that material, then it means its hardness is less than that of material. But if not, then it means it has the higher hardness as compared to that of the the material that we have used for scratching. So what does it gives? The ability of a harder material to scratch a softer material. Okay, so this is about the scratch hardness test. The second hardness test that we have seen was the rebound hardness. So let me draw the quick figure. So this is my hammer. This is my scale. It is at some initial height, let's say capital H. Okay, from the sample. So here, what we do in the rebound hardness test, we use a hammer and we drop it on the material. Okay, or the sample which hardness to be tested, and we will check the how much it has been rebound after dropping it. So this hammer, it is generally with a diamond rounded tip. Okay, so let's say if I have let it fail on the sample, means that indenter. So say this hammer fail on a sample. Okay, so then it will rebound. So it will rebound. Okay, so let's say this sample, this is my scale. Okay, so let's say this much my hammer with the distance of small h has rebound. So what does it indicate? So harder the material will be, the rebound height will be higher. So it means the harder material will give the higher rebound height. So and we can measure that value from the scale corresponding corresponding value of that edge. So the harder the material, higher the harder the material, a higher will be rebound. Okay, so it is very easy and it is portable. Okay, so this is the all about rebound hardness. Then we have seen the next hardness test, that is based on the indentation hardness. So what we do in the indentation hardness? So we indent a sample with an indenter, and then that indenter will make some impression, okay, or the indent on the sample, and then we will calculate its hardness by the using formula, that is load upon indentation area. So let's say this is my sample, okay, whose hardness I want to measure. So what I will do, I will take a indenter, okay, and I will apply a force on it. Okay, so let's say this is my indenter, okay, and I will apply a force on it. Okay, so what will happen? So this indenter will indent my sample. Okay, so let's say this much it has indentings. Okay, its corresponding thickness is, let's say, T1. Okay, and if I indent it more, means if suppose it has indented more, like, sorry, like this much, okay, that I have shown in the orange, then its indent thicknesses will be T2. Okay, so if we remove the indenter, we can see the indent mark. Okay, so here let me show by green color. So okay, so this will be my indent. Okay, so here also we can say that if the T1 is less than T2, okay, so we can say that the material, let's say the T1 is for T1 depth is for the material A, and the T2 is for the material B, then we can say that the A material has higher hardness as compared to that of the B material. So here we will see the indent. Okay, and how do we calculate its hardness? We calculate hardness by load upon indentation area. Okay, so now if we see the first indentation method, that is Brinell hardness. So what we do in Brinell hardness, we use a 10 mm steel ball or tungsten carbide balls. Okay, is used as an indenter. Okay, sorry guys, I have some issues. Just a second, let me. Okay, now it started working. Sorry, guys. So, is used as indenter. So, generally, the load that we apply is 3000 kgm. So, let's say this is my sample. Okay, let me draw it in 3D. Okay, let's say this is my sample, and if I indent it here, okay, so this is the spherical steel wall. Or tungsten carbide wall. So after indentation is done, if I remove it, okay, so we can see a impression on it. Okay, this is the impression by the ball. So if we measure the diameter here, that is, it's, let's say it is D1, and let's say along this it's D2, and our D is the average diameter, that is D1 plus D2 by 2. That is our average diameter. So in this case, the Brinell hardness, that is the BHN, the Brinell hardness number is given by the formula, that is 2p upon pi d. Sorry, it's pi d into d minus root d square minus d square. Okay, so here our P is the load that we have applied, and that in kgf. Then we have the D. This capital D is nothing but a indenter dia in mm. Then we have the small d, that is the dia of indenter impression, and that is in mm. So this is how we'll get the value of Brinell hardness number. So this method is generally not used for very high very high hardness material greater than of 400 because of that steel ball. Okay, so this may happen that the steel ball may itself get deformed. Okay, so this is about the Brinell hardness. Then after this, we have seen the concept. Let me write down that point as well for your better understanding. So, not reliable at high hardness value, and that is greater than 400. And it is also not suitable for the very thin samples. Why? Because this indenter will produce a larger impression. So, not very suitable for thin samples due to larger indent impression. Okay. So now after this, we have seen the second method, that is the Wicker hardness. So in Wicker hardness, what we use, we use a diamond pyramidal indenter. Okay, so let's say this is my diamond pyramidal indenter. Then the angle between this indenter is 136 degree. Okay, let me draw it in 2D as well. Okay, so this will be the indenter. Okay, and the angle between this one will be the 136 degree. And if we indent it on the sample, we'll get an indent something like this. Okay, the shape of the indent, I will draw it in the green. Let's say this is my indent impression. Okay, so in this case, let's say this is my D1 and let's say this is my D2, and the average of these two will be the my D, and the Vickers hardness number, the Vickers hardness or HV is given by formula 1.854 P divided by D square. So here our P is nothing but a loading kgf, and D square is nothing but a average diagonal length, and that too in km. Okay, so this is about the Vickers hardness. Then after that, we have seen the next indentation method, that is the Rockwell hardness. So in this we use a conical indenter. Okay, so we use a conical indenter, and the angle of that conical indenter will be conical indenter, and it will have an angle of this angle. Okay, it will be of 120 degree, and sometimes we use a steel balls as well. So we have the different scales of Rockwell hardness like A, B, C, and that depend the load and indenter type changes with the scale. Okay, so let's see how we calculate the hardness in Rockwell. So let's see. Suppose this is my material. Okay, whose hardness I want to check. Okay, so what we do, we first apply a minor load on the sample. Okay, so what will happen due to this minor load, that some surface irregularities it will take care of. Okay, so in A we apply a minor load. Okay, so it will give some depth. Okay, then after that we apply some major load. That so let's say we apply B. So in B we have minor load plus major load. Then we'll remove that minor load after some time. Okay, so this major load will produce some indentation depth. Okay, let's say this will be the indentation depth. Okay, then we will remove major load, and again I will get back to this position. C, remove major load. Okay, so then this height difference, that is E, indentation depth, will give me my hardness value. And how do we get that? That is hardness of a, if we use cone indenter, then we'll get hardness from this formula 100 minus E upon 0.002, or hardness for the ball indenter will get 130 minus E upon 0.002. Okay, so first what we do, I will write the steps here. So first apply minor load. Okay, then after this major load is applied and removed. Okay, so what will happen? Then we'll measure the final depth of indent is measured, and it gives the hardness value. Okay, so this is all about the hardness testing. Then after this we have seen the concept called the another testing, that is impact testing. So impact testing. So why it is done? Can anyone answer? So impact testing is done in order to analyze the material's behavior under a very high strain rate. Okay, and why is it so? Because the ductile material, if we see, they will show a brittle behavior under a very high strain rate, or we can say at a very low temperature they can show ductile behavior, and it considers the triaxial stress of stress, that is we provide a notch. So in case of tensile testing, the similar thing, but the strain rate will be not that much higher. Okay, and there we don't provide a notch, that is that we don't consider the triaxial state of stress. So that's why we need a impact testing. So why we do need? So we need, it is done in order to analyze the materials behavior under very high strain rates, or we can call it as impact loads, means sudden load, also we can call it as. And why it is done? Because ductile material tends to show brittle behavior under the conditions. The first one, that is high strain rate, also at low temperature and triaxial stress, or we can say it is notch effect. Okay, so we'll get a notch toughness or impact toughness. So how do we calculate? That is, if we are impacting some material, then the energy before impact is equal to energy after impact, and from that height difference we'll calculate the toughness value. And for this we have two different methods, that is the Charpy impact and Izod methods are used. And why is it so? Why these two methods are we use? Because they have a standard sample dimension as well as we have the notch stress concentration. Okay. So now if we see the sample size in case of impact testing, so let me draw. So here we will have V notch, okay, and the dimension will be the square cross section with dimension of 10 mm, and here we have the V notch with an angle of 45 degree and this length, okay, this is 8 mm. If it is 8 mm, then our notch length will be of 2 mm. Okay, so this is our sample for the impact test. So now what is the difference between Izod and Charpy? Okay, so let me draw the figure, then I'll explain. So Charpy, and here I'll draw the Izod. Okay, so let's say sorry. Sharpie ISO. So here you can see so let's say this is my sample and this is the notch, and let's say these are my anvils. Okay, so here somewhere I have hold my samples like this. Okay, so let's say, and here also as well I have hold my sample. And this is my hammer. Let's say this is my hammer, this is anvil, and this is my sample. So here you can see that the notch is in the opposite direction that of the hammer, and also it is that type of simply supported. Now if we see about the ISO, let's say this is my sample and I am holding it. Okay, so this red one, okay, here as well. Okay, so these are my anvils, and let's say this is the direction of striking of hammer. Okay, so this is my hammer. You can see that we have this notch in the direction is facing to that of the hammer. Here the notch is opposite to that of hammer. Okay, and here the sample is holded something like a cantilever beam type. So this is the main difference between the Sharpie and ISO. That is the sample position. Okay, so now this impact test can be performed at the different temperature. Okay, and it will tell the effect of temperature on the impact energy or the toughness of the material. So if we see that the people have done the experiments and they found a graph something like this. Okay, so on the y-axis they have the impact energy and here they have the temperature. So what they found, they found this S type of graph. Means with decrease in the temperature the impact energy is decreasing. So it means if I write it here, that is if T decreases, it means impact energy is decreasing. From this graph you can see. Okay, And we can see after a particular temperature here, if you see the point blue I have marked, so below that we can see the means the energy is very minimum, and we can see that below this certain temperature we will get a brittle mode of fracture. So below certain temperature, the mode of failure is brittle. So how do you determine whether the mode of failure is brittle or ductile? So from visual inspection also we can say if it is a granular and it has a surface has a shiny texture after fracture, and it has a cleavage, then we'll say this mode is of brittle fracture. And if it has a shear character and it has a fibrous structure and it has a dull character, then we can say that this mode of failure is ductile. Okay, so now in this curve, if I plot one more curve with this, that is the on y-axis, let's say this will represent my percentage of cleavage fracture. So we'll get a curve something like this, like for cleavage fracture. Okay, so here you can see that we have we'll mark some different regions with respect to that of the temperature. Okay, so let's say this is my first temperature here, that is this temperature is T1. So this temperature is known as FTP or fracture transition temperature. At this temperature, the probability of brittle fracture is negligible. Means it must always means it is almost fail with that of ductile mode of failure. Okay. Then we have the second temperature, which shows the this is here. Let's say this is my point T2. So what does it says? That it has 50% cleavage fracture and this and 50% brittle fracture, and this point is or the temperature is known as FATT. We can call it as fracture appearance transition temperature. Okay. Then if we take the average of upper shelf and lower shelf of the this curve, S curve, so we'll get a temperature somewhere around here. Okay, and this is my T3. It is the temperature average of this upper shell and lower shell. Okay, so now this is the third temperature. Now if I draw a temperature corresponding to 20 joule of impact energy, so let's say this is T4, temperature corresponding to 20 joule of impact energy, and this temperature is known as DTT, that is ductile transition temperature, and it is find out at 20 joule impact energy. Okay, and this is the temperature that we call as ductile to brittle transition temperature. And then we have the fifth temperature, that is T5. Let's say this is my temperature T5, and it is the nil ductility temperature, means the probability of ductile fracture at this point is negligible. So let me write down the different temperatures what I have mentioned. So T1 is, okay, let me make the two sections. So T1 is FTP or fracture transition plastic, or in other words we can say that probability of brittle fracture is negligible. Then we have the temperature T2, that is it has 50% cleavage fracture and 50% brittle, and we call this temperature as FATT, that stands for fracture appearance transition temperature. And we have the next temperature, that is the T3, which is the average temperature of upper and lower shell. So average, or we can say that temperature average of upper and lower shell. Then we have the fourth temperature, that is T4, that is nothing but a ductile transition temperature or DTT, and it is given at 20 joule of impact energy. Now the fifth temperature, that is the T5, that we have is the nil ductility temperature. So what does it imply? That is the fracture with almost no plastic deformation. That is probability of ductile fracture is negligible. Then after that we have seen the effect of crystal structure on DBTT. So we got one, we can see one graph here, that is here on x-axis we have temperature and on y-axis we have energy absorbed. Okay. So here we can see that we have 1 hour, that S-shaped curve, and then we have this curve for FCC and SCP materials, or we can say that for low strength material. Then we have this curve for generally for BCC material, and also we have seen one more curve, something like this, that is for high strength material. So the low strength and high strength material generally, that is FCC and FCC and SCP, don't exhibit a DBTT, while the BCC exhibit a DBTT. So this is the effect of crystal structure on DBTT. Okay. So in the last, we have seen the new concept, that is the mechanical behavior of composites. So mechanical behavior of composites. Okay, so mechanical behavior of composite. So what is composite? It is consist of two distinct phases. One is the matrix and second one is the reinforcement. So it can be two or more than two. So consist of distinct phase, two or more. So among this, one is the matrix and second one is the reinforcement. Okay, and why do we make composite? That is to increase the elastic modulus. Okay, and the elastic modulus should change significantly after the addition of the reinforcement. It means elastic modulus should change significantly upon addition of reinforcement. And this is about the composite. Now if we see the characteristics, so it depends on the various factors. So the characteristics of composites, so depends on characteristics of the composite depends on, the first one is the matrix. And what are its role? So if we see the role of the matrix, so then it provides the bulk form. Okay, it is available in the bulk form in the composite. So provides bulk form. Then it protects the reinforcement. Then the third one is the it transfers the load to the reinforcement, means transfer of load to reinforcement. And the fourth one is the partial deformation. So these are the roles of matrix, and it influences the characteristics of composite. The second one that influences the characteristics of composite is reinforcement. So what are its role and how does it influence? So it carries the major portion of load. And second, it should bond well with the matrix. Means it should have a uniform, or it should have a strain continuity. Means for strain continuity. Okay. So these are the factors that affects the characteristics of composite. Okay. Then after this, we have seen the types of composite. So what are those? So we can classify composite depending on, first one is the based on matrix, means which matrix we have. So it can have a metal matrix, it can be of ceramic matrix, and we have polymer matrix. Depending on the class of material, this classification has done. The second one is the based on the distribution of reinforcement, means how the reinforcement is distributed inside the composite, means based on distribution of reinforcement. So this depends on, the reinforcement can be continuous or it can be discontinuous. Then the third type that we have, differentiated composite, that is the based on the type of reinforcement. So type of reinforcement. So in this we can have particle reinforced composite, means particle reinforced. We can have a continuous fiber reinforced composite. We can have a short fiber, or we can also call it as viscous. And also we can have a laminate composite, means the best example of laminate composite is plywood. And also we have a fourth type, that is carbon-carbon composite. So this is the different types of composites that we have seen. Okay. Now if we see the strengthening of a composite, so strengthening of composites. Strengthening of a composite. So the composite can get a strengthening by two effects. One is the direct strengthening and one is the indirect strengthening. So strengthening can be of two types. One is the direct and second one is the indirect. So in direct strengthening means due to the direct transfer of load. Due to direct transfer of load. And in indirect strengthening, it is due to change in microstructure, or we can say and properties, and that is due to addition of reinforcement. Now, then after this, we have seen some elastic properties of composite. Elastic properties of composites. So, the elastic properties of composite, if we see the first property, one is the mass. So, the mass of composite MC will be equal to mass of matrix plus mass of reinforcement. The second, that is the volume. So volume of composite will consist of volume of matrix plus volume of reinforcement, and there might some porosity or voids will be present. So that is we know. Similarly, if we find out the density of a composite, so it will be equal to mass of composite divided by volume of composite. And if you find out in the form of fraction, then it will be equal to Fm rho m plus a fraction of reinforcement into density of reinforcement. So this way we can determine the elastic properties of the composite. So now if we say, like, if we are loading any composite, so how do we calculate? So it's Young model. So we have two mode. One is the isostress condition, and second one is the isostrain. So let's say this is my composite. Let me show. So here I have applied some load P, and here also I have applied with some load P. And so in this case, the stress on my composite will be uniform throughout. So it means that's why we call it as isostress model. So if I draw the spring model, so this is P. Let's say this is for my matrix M, and this is for my reinforcement R. Here also I have applied. So in this case, the Young's modulus EC dash is given by EM ER upon FM ER plus FR EM. Okay, and it is also the lower bound. Means this is the minimum value that we can get. So this is lower bound, and this is known as Rolle's model also. Then we have the second condition, that is the isostrain condition. Okay, so let's consider let's say this is my composite and it is loaded like this. Okay, so in this case the stress is not uniform, but the strain in the each laminate, or we can say the strain is uniform. So if I draw the spring model, so it will be something like this. Like let's say this is P, this is for my matrix, this is for my R. And the Young's modulus of the composite is given by Fm Em plus Fr Er. And this is the upper bound. And this model is known as white model. Okay, so this much things we have seen in the week 12. Okay, so any doubt till this point, guys? In quick recapitulation, as this will be our last live interactive session, if you have doubt, please clarify it before the exam. Okay, so I am just showing what are the things we have covered. So we consider we have seen the hardness testing. Then what are the different types like scratch, Brinell, scratch, rebound, and indentation. And in indentation also we have seen the Brinell, Vickers, and Rockwell hardness test. Then we have seen the impact testing. Then what are the different types of impact testing, and what is DBTT. So how to identify the brittle fracture and ductile fracture from the visual inspection. Then we have seen the effect of crystal structure on DBTT, and in the end we have seen the mechanical behavior of composite. And in that we have seen the what is composite, characteristics of the composite, then the types of different composite and what are the strengthening mechanism in the composite and the elastic properties of the composite. And also in that we have seen the isostress and isostrain model. So this is the quick recapitulation of the week 12 content. So now we can move towards solving our assignment problems. So here is the first question of the assignment 12, that is the Brinell hardness uses. Please try to answer this, guys, it's very easy. So please try to answer it. Okay. So now, if we see in the Brinell hardness, we use steel ball or tungsten carbide ball, and that is of 10 mm. Okay. Then we use in Vickers we use diamond pyramidal indenter, and the angle of it will be 136. And Rockwell we use diamond cone, or we can use ball as well. Okay, and the angle of cone will be 120 degrees. So now they are asking about the Brinell hardness. So in Brinell hardness, we use the steel or tungsten carbide ball. Okay, so here we have the option tungsten carbide, steel sphere, diamond cone, and diamond sphere. So these two options we can eliminate. Okay, so remaining two options. One is the tungsten carbide and the steel. So here we are using the ball. Okay, and it has a shape of spear. So it means it is not a cone. And here they have written tungsten carbide cone. So the correct answer will be our steel sphere. Is it not? Now moving towards second question. So in a hypothetical curve given below for impact testing, the correct combination for A and B are. So they are asking you to determine the which curve belongs to which material. Please try to answer it, guys. So in quick recapitulation also we have covered this part. So from that also you can answer. Just you can refer to that section and you can answer. So okay, let's solve this. So we have seen that this graph is for generally for FCC and SCP material, and this one belongs to the BCC material. Okay. So now from the given option, if we find out different metals, so we have mild steel, then we have copper, then we have nickel, and we have low carbon steel, then we have chromium, and we have aluminium or authentic steel. So if we write this crystal structure, so mild steel will have BCC, copper will have FCC, nickel will have FCC, the low carbon steel so nickel will the chromium will have the low carbon steel again will have BCC, the chromium will have which structure? It will have BCC, the aluminium again it has FCC, and austenitic steel means gamma steel, it has FCC. So now try to answer it. Okay, please try to answer it, guys. So let's check one option one by one. Okay, so A mild steel and B is copper. So the mild steel has a BCC. So it means this option itself is a wrong. From the beginning itself we can see. Okay. Then we have A is nickel. So here we can say is nickel. Nickel is FCC. And it means this first part is correct. Then B is low carbon steel. Then we have B is low carbon steel and that belongs to FCC and this is BCC. So this one is correct. Okay. Then we have A is chromium. So here we can see that the chromium has a BCC structure. It means the first part itself is wrong, means this answer is also wrong. Now we have second part, that is A is aluminium. A is aluminium and aluminium has a FCC structure. So first part is correct. Then B is chromium and chromium has a BCC structure. So this part is also correct. So this, how you can answer this question. Okay. Now moving towards third part. Please try to answer this question. Now please try to answer this. This part we have covered in the lecture itself also. This part has been covered in the lecture as well. So you can refer to that and try to answer this question. So please try to answer it. So first I will write down like how to identify the brittle and ductile fracture. Okay, if it is granular and it has a shiny texture and it has a cleavage, then this fracture is brittle fracture. Then if it has a shear character or the fibrous structure or it has a dull character, then it is a ductile fracture. So if same material we are testing, so the brittle fracture will happen at a low temperature and this is comparatively high. Okay, so this is high temperature. Okay. So high temperature in the sense it can show ductility at room temperature as well. Okay, so if that material is showing at room temperature, so it can show brittle fracture at a lower temperature. So that's why this is the relative term I have used. So now if we see here the first one, T1, so the surface is shiny texture, it is following T1. Then we'll see the T2. So T2 also has a shiny surface. Now, if you go to the T3, then T3 is having some dull surface, means there is T3. So it means T3 should be greater than T2 comma T1. Is it not? Yes. Now among this, if we see, that T1 shows the somewhat higher cleavage. So it means T1 should be less than T2 and it should be less than T3. So the only option this satisfies this condition is this one. So the option 1 will be the correct answer to this question. So now coming towards next question, mark the correct statement. So NDT is defined as the temperature below which fracture is 100% brittle. And FATT is the temperature where fracture is 50% ductile and 50% brittle. And FTP is the temperature above which 100% ductile failure is observed. And the ductile transition temperature is a point where impact energy is 20 joule. Please try to answer it. So for your understanding, I will draw the figure, and from that figure also you can easily answer. This temperature, this is percentage cleavage fracture. Here we have the impact energy, and we have curve something like this for impact energy versus temperature. And if I plot a curve for percentage of cleavage fracture with the temperature, so this one will get this curve for cleavage fracture, and this black one is for the impact energy. Okay, so here we have first temperature, that is T1. Then we have a second temperature here, and T2, and corresponding fracture is 50%. This point is also known as FATT. Then this point is known as FTP. Sorry. And then we have the next temperature, that is here. That is the average temperature of upper and lower shell, and it is T3. Then we have the next temperature, that is here at 20 joule, and it is our T4, that is DTT. And we have our last temperature here, that is T5, where we have a brittle fracture, and here we have a ductile fracture. So now from this curve you can easily answer the question. Or we can call it as NDT. So the first statement they have given NDT is defined as the temperature below which the fracture is 100% brittle. So this is true. So below this temperature, the fracture will be brittle. So this is the correct one. Now the second, FATT is a temperature where the fracture is 50% ductile and 50% brittle. So now if you see FATT, so this is the, if it is a 50% ductile, means remaining is the brittle. So this one is also correct. Now FTP is a temperature above which 100% ductile failure is observed. So above this temperature, like this temperature, we can get a 100% ductile fracture. So it means this is our fracture transition plasticity temperature. This is also correct. Now the ductile transition temperature is a point where impact energy is 20 joules. So it is correct because we defined the DBTT at a impact energy of 20 joules. So this is also correct. So it means all four options are correct. So now moving towards next question. So find the Brinell hardness number if the load is 200 kgf. The indented diameter is 1 centimeter and the diameter of the indent impression is 0.2 centimeter. It's very easy question. Just 1 or 2 minute question you can answer. Anyone? Let's try to answer this, guys. Okay. So we'll solve it together. So BHN is given by equation 2p pi d into d minus under root of d square minus d square. So here our P is load in kgf, D is the indenter dia and small d is the impression dia. So in this question they have given us the all the things. This is our P, this is the indent diameter is 1 centimeter, means it's D, and the indent impression is, means diameter of indent impression is small d. So we have all the value, just put the value and get the answer. So we have BHN is equal to 2 into load is 2000 divided by pi into all these things are in mm. So we'll get pi. D is how much? 1 centimeter. It means 10 mm into 10 minus underscore under root of 10 square minus 0.2 is 2 square. So now tell me the Brinell hardness number. So I will calculate as well. 2 into 2000 divided by 6 pi into 10 into and so 10 minus 10 square minus 2 square. So this will give me the value of 630.2. 630.2. So the option matching to this value will be 315, 630, 452 and 530. So 631 is very close to our answer. So this is the correct answer. Okay. So now moving towards next question. So the question is like that. Apart from the impact and hardness tests discussed in the lecture, compression tests are typically carried out to measure the compressive properties of the metal and alloys. So in a compression testing, so if we take a block of initial height h0, then we can compress it to a height of h1. Then the axial compression strain will be given by the formula, that is epsilon is equal to integration of dh upon 1 by h and limits tending to h0 to h1. This is the true strain. And for engineering strain, we have E is equal to h1 upon h0 minus 1. Okay. So they have given the equation and they have given the height as well. So they are asking now, if during the compression test a cylinder is compressed from 30 mm to 10 mm, the magnitude of true strain is. So please try to answer this question. And remember, the calculated strain is negative for compressive strain. So but we have reversed the metal work. We have reversed the conversion. So all the things has been given here. So please try to find out the answer. Anyone?
It's 1.09.
Yeah, Mr. Sorry. Hello.
1.09.
0 point
1.09.
1.0. Okay, we'll solve it together. Okay, so here we know the true strain is given by minus ln h0 upon h1. So we have the where h0 is the initial height and hf is the height after compression. So the initial height here is given as 30 mm. So this is our h0 and this is 10 mm is height after compression. So this will be our h1. So minus ln, we have 30 by 10. So if we find out, we'll get an answer somewhere around minus 1.09. So, but in the case of metalworking, we define the stress and strain as positive. So if we represent it as positive quantity, so it will be 1.09. So the correct option will be the first one. So you are right, Mr. Muthu. So now moving towards next question. That is the, yeah, any doubts?
Oh, no.
Okay. So the purpose of matrix phase in the composite is to, they have given the 4 option and you try to answer it. So in the quick recapitulation in the very beginning, I have covered this part. So you can refer to that and you can answer. So for this question, in the recapitulation, we have seen the characteristics of the composite depends on mainly on the matrix and reinforcement, and in that too we have listed down the some roles of composite, for the matrix material. So for matrix, what are the roles? So it should provide a provide bulk form. The second one is it should protect the reinforcement. Then third one, that is it should transfer the load to the reinforcement, means transfer of load to reinforcement. Then it should bind to the reinforcement. If the binding is not good, will not get the desired properties. Then we have in the last, that is partial deformation. So these are the roles of matrix. So now if we see, the first option is the share the load to the reinforced material. So here we have that option, that is the transfer of load to the reinforcement. It means the matrix should share load with that of the reinforced material. So this is first one is the correct one. Now bind the reinforced material. Yeah. So we need a matrix material to bind the reinforced material so that we can get the enhanced properties. So this is also correct. Now deform partially for effective load transfer. So if in order to load transfer, the material should partially deform. So these three are correct. Then improve the Young's modulus of the composite. So the Young's modulus will be improved after the combination of matrix plus reinforcement. So this is not alone the purpose of matrix. So this is not correct. So only first three options are correct. Okay. So now coming to the next question. Any doubt in this question, previous question? So moving towards next question. So we have, in a situation where we want a good insulation on the material and surrounding is chemically active, then which type of composites are most suitable to use? Please try to answer it. So generally, if the surrounding is chemically active, the metal and alloy can easily react with the chemical. So this will not be the good choice. This chemical and alloy. The remaining is the polymer and ceramic. So the ceramics are generally the inert one and they don't react with the chemicals. So this one will be the wise choice, first one. Now what about the polymer? So in polymer, this also reacts like with the epoxies and all these things. So this can also react. So this is also not a good choice. So we'll use a ceramic matrix composite. Now coming towards next question. So the if it is a given that in composite volume fraction of a matrix is 0.79, while the volume fraction of the reinforcing phase is 0.19, then which of these is true? Anyone?
Together it should be one, but it is
Okay. You are saying it's one. Okay. Let's see. So here the sum of the volume fraction should be equal to 1. Okay. So let's say Fm plus Fr should be 1. It means here we have 0.79 plus 0.19, which is not equal to 1. It means we have 0.02% of error. So if you see the matrix, okay, so let's say this is my matrix, okay, and let's say this is my fiber. Okay, I am considering the case of fiber. So this is my fiber or reinforcement. So suppose the bonding between them is not good. Okay, so what will happen? They will try to create a voids. Okay, and it will have some volume fraction. So now we'll check one option one by one. So the remaining volume fraction of 0.02 is a void which gets created when the matrix and reinforcement are combined to form a composite. So this case we have already discussed. It means this one is correct. Now coming to the next part. Such a composite is not possible as the sum of two volume fraction must be 1. So this is not the case. Okay. So ideally we can say that, but actually there might be some void formation and also they are creating the composite. So this one is also not correct. So it is possible that the composite has other matrix which accounts for the remaining volume fraction. This is also not correct. And in the last that we have discussed this part in the quick recapitulation, it means this is also not correct. Okay. So now moving towards the next question. So the question is like that: a composite is made using fiber reinforcement and a load is applied along the axis of a cylinder. It is given that they have given the values of Young's modulus of matrix and reinforcement, and they have given the volume fraction, and they are asking us to calculate the Young's modulus of the composite and in the longitudinal direction. So what will be the answer?
it is 125.
Okay, 125. So any other option? Anyone? Okay. Okay, let's see. So suppose they are asking us to load in the longitudinal direction. So this is our longitudinal direction, means along the length. Okay. So in this case, the reinforcement is getting the same strain as that of the our matrix. So it means the strain is same. This is the condition of isostrain. Okay. If the strain in the reinforcement and the matrix is same, then that condition belongs to the isostrain. And for isostrain condition, we know the Young's modulus of the composite is given by EC equal to fraction of matrix into Young's modulus of matrix plus fraction of reinforcement into fraction of modulus of reinforcement. So if you use this formula, we'll get that the volume fraction of fiber is 0.25. This means this is our FR, and Fm plus Fr should be equal to 1. So Fm should be 0.75. So 0.75 into EM, they have given EM is 1000 GPa. So 1000 plus ER is 200, and the reinforcement has a volume fraction of 0.25. So 200. So if we calculate, we'll get value somewhere around 0.25 into 200. So let me check the answer once again. Oh, sorry, it's 100 GPS. So the correct answer will be, sorry, my mistake, I took 1000. It will be 100. So this will be 75, and this one it will get it will be around 125 GPa. So the correct answer will be this last one. Okay. So this is the end of our assignment 12. So now we'll discuss one more concept related question, and after that we'll end our session. Okay. So here this question is like that: the sketches in the figure below show the pair of dislocation that are about to intersect. The arrow show the direction of motion, and they have given dislocation A and C are moving into the paper, and the dislocation B, D, and F are moving out of the paper. So they are asking you to sketch the how this dislocation interact, and they are asking the nature and character of that the steps that has been formed. So please try to answer it. So to answer this question, we should know how two dislocation interact. So if the two dislocations are interacting, so the one dislocation will create a step in another dislocation, and that too in the direction of the Burgess vector of first dislocation, and its magnitude will be equal to the magnitude of first dislocation. So this will create a step. Now the character of this step will define. So if the line vector of that step and the Burgess vector are perpendicular or parallel, from that will define its edge or screw character. And whether it is a jog or king, that will define from the plane. If it is in the same plane, then it will be king, and if it is the out of plane, then it will be the jog. Okay, so let's see here. Okay, so let's consider this is case A, B, and C. So they are saying the dislocation A and C are moving into the paper. So this will be the direction of Burgess vector of A. Okay, that means it's going inside the paper. Whereas B is coming out of the paper, so this will be the direction of B vector. Is it not? So now, if we plot, if we consider the case A, okay, let's say this is my plane. Okay. Let's say the dislocation A, let's say dislocation B intersect with the dislocation A. Okay, so this B is intersecting with the dislocation A. So this will create a step something like this. Is it not? So let's say this is my one dislocation creating step here. Okay, so this is my A dislocation. Okay, and this is the direction of Burgess vector of dislocation A, and let's say this is my step SA. Now this, if now consider the second case, this dislocation A will create a step in a dislocation B in the direction of Burgess vector of dislocation A. So in this case, it will create a step something like this is B. Okay, and the direction of Burgess vector is this one. Let's say this is my SB. Okay, so now if we see here SA, okay, this SA, and the line vector is parallel to that of the Burgess vector BA, means SA vector is parallel to BA vector. It means it has a screw character. Similarly, here you can see for SB vector, this B vector is parallel to this BB vector. So it means they have a screw character. And as this two dislocation after intersecting are not changing the planes, it means these steps are nothing but a kings. So these are kings. Now try to solve for the case 2. So the step formed in SD has a which character in case of B? So here the D dislocation is moving out of the paper and it is the H dislocation. So this will be the Burgess vector of D dislocation. The C dislocation, here you can see it is a screw dislocation and it is moving into the paper. So the left side will be the direction of Burgess vector of C. Okay. So now if we draw the intersection, then let's say this Burgess vector B is creating step inside a dislocation D in the direction of Burgess vector of C. So this is my initial dislocation line at D. Okay. So now it is moving towards the left. So it will create a step in the left side. And again, this is my the remaining dislocation. Okay. And the step created here is SD. Okay. And the direction of that of our D location is this one. This is the Burgess vector direction. Okay. Now consider this D dislocation will create a step in C in the direction of Burgess vector of D. So let's say this is my original screw dislocation. Okay, so this is the direction of Burgess vector D, means it is going inside the paper. So it creates step here and the remaining dislocation will be the same. So this is my C dislocation and the Burgess vector will be this direction BC. Okay, and this is my segment ESC. Now if you see here the segment D SD, so this is segment SD and its line vector is perpendicular to Burgess vector BD. So line vector of SD is perpendicular to Burgess vector of, it's perpendicular to Burgess vector of BD. So this has a H character. Now similarly here you can see SC is perpendicular to the Burgess vector of C. So means SC is also perpendicular to Burgess vector of C. It means it also has a H character. Now here you can see that this SD is changing its plane. Means SD is changing the plane of dislocation. So initially this blue, dotted blue was the plane of motion. Now this is the new plane of motion. This orange one. Okay, so this orange one is the new plane of motion and this blue one, dotted blue one, is the old plane of motion. So this SD is nothing but a jog. Okay, so, and similarly see the glide plane remains same. It means this step is nothing but a key. Now try to draw it for the third case, that is the C. Both are the screw dislocation. Anyone? What are the character of the steps and whether it is jog or king? So E is moving inside the paper. So this will be the direction of Burgess vector of E, and F is moving out of the paper. So this will be the direction of Burgess vector of Burgess vector A. Okay. So now both are the screw dislocation. Okay. So first we'll draw the plane. Okay. So now let's consider our dislocation F first. Okay. So this is my dislocation F. Okay. So now this E dislocation is intersecting with the F dislocation. So it will create a step in the F dislocation in the direction of Burgess vector of E. So it is moving towards left. So it will create step this side. Okay. And this is the remaining one. So this is my dislocation F. And the direction of Burgess vector will be this downward. This is BF. Now consider the second case. Okay, so this is my E dislocation. Okay, so now this this F will create a step in a E dislocation in the direction of Burgess vector of F dislocation. So it is moving down. So this is the step form. So the step is somewhere downwards. So this is my E dislocation, and the direction is this one, BE. Okay, so now this is my segment SF and this is my segment AC. So now here you can see that the line vector of SF is perpendicular to Burgess vector. So SF is perpendicular to Burgess vector. It means it has the H character. Similarly, here AC is perpendicular to B, means AC vector is perpendicular to B vector. So means this step also has a H character. And as these two steps are changing the glide plane, so these are nothing but a job. Okay. So this was one concept related question. So we'll end our today's session here itself. So thank you everyone.
Thank you.
Yeah. Okay. This was the last session. So I am in today's session. Thank you.